Welcome back. Our next lecture is on reactions. Now, we're only going to focus on two types of reactions. One goal is to be able to predict hydrocarbon halogenation reactions. And the other goal is to be able to predict hydrolysis of esters and amides. So let's look at the halogenation of hydrocarbons. So for alkanes and cycloalkanes, they halogenate the same way. So here I have a very simple alkane, the simplest you can have, and we're going to halogenate it with chlorine, which is a halogen. For this reaction, you need light. It will not take place in the dark. Now, what happens here is one of the hydrogens gets removed and you put a chlorine there instead. That hydrogen that gets removed combines with the other chlorine to make hydrochloric acid. This is called a monochlorination product. Now, the interesting thing about this is that this molecule can also react, and a hydrogen can be removed and a chlorine added. So you could get CH2Cl2. And this could continue until you replace all of the hydrogens on the methane to get CCl4, which is called tetrachloromethane. So this is considered to be a monochlorination product, a dichlorination, a trichlorination, and a tetrachlorination. And if you put these two things together, you would get all of these products because the chlorines don't check to see how many hydrogens are on the methane. It just reacts with the hydrogen. It's very indiscriminate. So this is not a very useful reaction, but this is a this is chlorination of alkanes and cycloalkanes. Same thing would happen with cycloalkanes. The hydrogen gets removed, the chlorine gets added. This could also happen with bromine, where a hydrogen gets removed and a bromine gets added, and you make HBr. Okay, so this is halogenation of hydrocarbons. Now, let's predict all of the products of all the dichlorination products of propane. So here, dichlorination means that we're going to get two chlorines attached to this. What are the places where there are hydrogens? Well, take a look at this first carbon. How many hydrogens are there? There's 3. So we could actually get 2 chlorines here where 2 of the hydrogens are removed. Now, another molecule, you could get 2 chlorines on the second carbon, or you could get 2 chlorines on the third carbon. Let's find out if we have 3 different products here by naming them. This one is called 1,1 dichloropropane. This one is called and I made a mistake. It's called 1,1 dichloropropane. This one is 2,2 dichloropropane. And this one is not called 3,3 dichloropropane. It's called 1,1 dichloropropane. Because when we start naming this, we want to start at the end closest to the branching. And so we're going to call this carbon 1. So these guys are the same thing, and this is not a different product. Now, let's see if there are any other dichlorination products we could have. Well, could we have a chlorine here and a chlorine here? You bet your Bippy. What would that be called? Well, that one would be called 1,2 dichloropropane. Now, are there any others? And the answer is, I think so. We could have this one here, which would be called 1,3 dichloropropane. And that's how you go figuring out all the different products. You try to do it very methodically. Do you see what I did? I put both chlorines on the same carbon if I could. And I went through all the permutations. I named them to see if they have different names. If they have different names, they're different products. And then after I did all the permutations where all the chlorines are on the same carbon, I said, well, I'm going to keep one on the first carbon and then move the chlorine onto other carbons and see if I get something different. And here's what you get. Okay, the next reaction we're going to look at is halogenation of hydrocarbons for alkenes and alkynes. Now, this is a very interesting reaction because you'll notice here it can occur in the dark. We don't need light to make this happen. Secondly, you'll notice that the chlorine, both of them add to the alkene. Both chlorines add. We don't get any HCl. Third thing you're supposed to notice is that one chlorine adds to one carbon where the double bond is. The other chlorine adds to the other carbon where the double bond is. And so here's your product. Same thing happens for alkynes. So you'll notice that I have a triple bond here. One chlorine adds to this carbon and one adds to this, and we get rid of a double bond or a pi bond. And then we have a double bond here, so this can react and we get that. So the deal is that this particular reaction reacts with pi bonds. For every pi bond, 2 chlorines add. So let's take a look at halogenation of hydrocarbons for aromatics. Here, these look like double bonds and I'm adding chlorine to this, but there's no reaction here because these guys are not really double bonds. If you do want to get this to react, what has to happen is you have to add a catalyst. So iron 3 chloride is the catalyst in this case. And I drew the hydrogen here so that you can see that what happens is that hydrogen gets pulled off and one of the chlorines gets attached. So what happens to that hydrogen? It attaches to the chlorine and you get HCl. So this is halogenation of hydrocarbons. And this is something that usually also takes heat. So kind of to sum it all up, we have, okay, let's predict the outcomes of the following reactions. So here, you'll notice that we don't have any light here. What's going to happen here is the following. So I draw the parent chain just like this, and I don't draw the double bond. I'm going to put a bromine on one side of where the double bond was and a bromine on the other, and there's my product. Now, this is happening in the dark. This is a catalyst. So what's going to happen with this? Well, turns out I could get a number of different products. I could put a bromine here. I could put a bromine there. I could put a bromine there. So one on that carbon, one on the carbon next to it, one on that one, plus I could get one more. I could get a bromine opposite of that. Now, what would happen if I put a bromine there? It'd be the same as this one. If I put a bromine there, it'd be the same as that. So I could actually get 4 different products here. Now here, I don't have a catalyst. What's going to happen here? And the answer is the following. This is not an aromatic carbon. It is an alkane carbon, and the bromine could add there, plus I would get HBr. Now, for each of these, I would also get HBr, so we don't really care about that. So there we go. You'll see a problem like that on your homework, or problems like that. So, reaction of an alkene, draw the structure of the compound obtained from the reaction of Br2 with propene and name the compound. So here's propene. Propene means it's got a double bond. Prop means it's 3 carbons long. And we're going to add bromine to it. So there's your product. I put a bromine on carbon 1 and a bromine on carbon 2. Okay, lastly, we're going to look at something called the hydrolysis of an ester or an amide. The deal with the hydrolysis of an ester is that when you add water to it, you can break this bond here and turn this into a carboxylic acid and an alcohol. With an amide, you do something similar. You can break this bond here and you can turn this into a carboxylic acid and an amine. So here's the key to recognizing how to do these problems is the bond that gets broken is this bond right here. So here you can see I've separated the two. And you always add the OH to the carbonyl, and you always add the H to the other side, and that's how you get your product. It's the same for the amide. You break this bond here between the carbonyl and the nitrogen, and you add the OH to the carbonyl and the hydrogen to the nitrogen. So here you can see that we break that bond, add the OH to the carbonyl, and add a hydrogen to the nitrogen. So let's take a look at a couple of problems based on this. Predict the outcomes of these reactions. So here, what I'm going to do is I'm going to redraw this, but I'm going to break it. I'm going to show you where the bond breaks. So it's going to break right there. It always breaks between the carbonyl and the oxygen. Okay, so we got that. And where do we add the OH? Always to the carbonyl. Now here, I'm going to add an HO because the oxygen bonds to the carbonyl. And here, we're going to put a hydrogen, and that's it. So this one becomes even more interesting. Where does this break between the carbonyl and the nitrogen? You'll notice that I kind of made this a little different so that I could separate the things. What always adds to the carbonyl? The OH by the oxygen, and then the H to the other side. So this is an interesting molecule. We start off with one molecule and we end up with one molecule. However, this molecule is a ring. This one no longer has the ring. So we've broken the ring. So you will see some problems like that on your homework about how do you hydrolyze things like this. You'll also see this in a lab that you'll be doing. Well, that you'll be watching. Okay, thank you for listening. Toodles.